So yesterday we did that well ordering principle and induction, right? So the next thing is divisibility. So that is fine. So here, so if n d divides n, so we'll use the notation d slash n. So that is the meaning is that n I can write it as c times d for some c, right? And if d does not divide n, then we'll use the notation that d does not divide n. Okay,
Yeah.
right. So now some properties are there. So the thing is, it is transitive, right? The the divisibility relation is transitive. That is what I mean is, suppose d divides n and n divides m. So this will imply that d divides m also, right? The second one is linearity. So linearity is suppose d divides n and d divides m also. So this will imply that d divides a n plus b m, right? For some a and b, right? Right?
A N plus B N.
Yes, a and b are integers. Okay.
For example, B equal to 0.
Yes, d is divisibility. We are not taking zero because division by zero it is not defined, right? Yes, you can take anything
A
other than
B equal to 0 or not? Not.
d cannot be zero because division by zero it is not
Not the A B.
ab. Yes, yes, ab can be zero. Yes,
Because B equal to 0, that's the makes sense. But
yes,
if
yes,
B not equal to 0,
yes. So let us see an example.
mm,
So for example, 2 divides 4, right? And 2 divides 6 also. So this implies I can that 2 can divide 4 plus 6 also, right? So here a and b I am taking 1.
mm,
2 divides 10, right? So that is true, right?
mm,
Here I am taking a equals to 1, b equals to also 1.
mm.
Okay.
Yeah, yeah.
Yes. So generally you can prove also. The thing is d divides n implies n equals to c times d. Similarly, you can take
Mm,
something for m and then substitute here and prove it, right?
mm, mm, mm.
Right. So the next property is multiplication property. So it says suppose d divides n. So this implies a times d that also divides a times a, right? N,
Yeah.
right? The fourth property is cancellation law. Suppose ad divides an
Mm,
and a is not equals to 0. So
mm,
this implies we can cancel the a and write d divides n,
mm,
right? The fifth one is that one, the universal law for 1. So 1 divides n for every integer n.
mm,
And sixth one is n divides 0 for every integer n.
mm,
Okay. So next observation is if d divides n and your n is not equals to 0, then the it is less than equals to n. The mod value
Mm.
of d, the mod of d is less than equals to mod value of n.
Mm.
Okay, means it's a in modulus in the absolute value sense,
Mm.
the value of d must be less than equals to the value of n, right?
Mm. 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 Yeah, yeah.
So the next one is suppose d divides n and n also divides d. So this together only implies that d has to be equals to n,
Mm.
or you can say that mod of this thing, because plus minus we can differ.
Mm.
Okay. So now, so the last point is suppose d divides n and n is not equals to 0, then n by d is an integer, right? So that will also divide,
Mm. D in the N over the okay. Okay.
right?
Mm.
So that is because so n equals to some c times d, right?
Mm.
So here c equals to n by d, right?
Mm.
So this will also imply that c also divides n, right?
Mm.
That's why this is the condition.
Yeah, yeah, yeah.
So I
Mm.
think up to this is fine. So
But
this is the,
this is about modulo is right. So
yes, divisibility
I
conditions.
recall something about maybe the definition of positive modulo and negative modulo is different. Not the same.
Uh, yes,
Not
positive.
how to was previously I think so. For
Okay.
example, three minus one minus two. Hmm.
Okay, we'll come maybe to that to the later.
Mm.
Right.
For example, the remaining is right. If the divides by n, so that's okay for negative and positive.
Yes,
But
yes, that is not a problem.
if
Then
we
then
have
it's
remaining something cause, yeah, yeah,
okay.
yeah, yeah.
So this is the divisibility condition. So the next thing is the greatest common divisor.
Hmm. GCD, yeah.
Right. So greatest common divisor, what is saying? So that if suppose d divides a and d divides b, then d is a common divisor
Hmm.
of a and b, right?
Yeah, yeah.
So that is fine. So now the next theorem is based on this. So what does it say? So it says that given any two integers a and b, there is a common divisor d of a and b, so of the form such that we can express that as d equals to ax plus by, where a and x and y are integers. X1 y belongs to z, right?
Hmm.
And moreover, every common divisor of a and b divides d. Right. So let us try to. The statement is clear, right? So
Wait.
yes, read it
Two
once.
integer IP common division D. Hmm. The form of common division is D equal to AX comma
Right.
B1. Yeah. Hmm. Hmm. XY can be negative.
Yes. So ax plus so this the divisor that will depend upon a and b, right?
Okay, XY can be negative. Yeah.
Xy can be negative, yes. So usually we will see later that x and y both are not negative. Usually one is negative and one is positive, but that will come. That will come later.
So if SY can be negative, we can say that with every a every IBD we can always find S and Y. So the search D is common. Is
Mm,
because A is equal to minus BY. So the right hand side is 0.
okay. Yes, but yes, the divisor we want not equals to zero, right? Because division we are not. D is not equals to zero.
D not equal to 0, but the right hand side equal. Uh,
Yes, but we don't want D to be zero, right?
uh, 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 mm, yeah. Mm.
Okay.
So x and y not equal to 0 is right.
X and Y, yes. X and Y is not
Should
equals to zero.
be should be not equal to 0 because if it's 0,
Yes,
we
then D
cannot
cannot
say
be a
about
common divisor.
common divisor. For
Yes.
example, y equal to 0, so d equal to a is. That mean a and b is not have common division.
Yes.
You- Moreover, every common divisor of A and B divides B. Yeah. Mm,
Yeah, that will come, but let us we have to prove.
mm, mm, mm. We can see some example first.
Example, okay.
And not yet every common divisor of A and B divide D. That's
Yes.
mean S and Y divide B.
No,
Divide
not
D.
X and Y. I am saying, so here it is saying that every common divisor of A and B that
Other.
will divide D.
Uh, D is also a common divisor. But
Yes.
other divisor should divide the.
Yes, that is they are saying.
Oh, yeah. I guess it and understand, but have not imagine an example for that.
Yes. So, for example, is okay. So, if you want an example, let me think of an example.
Mm.
Okay, 1 minute. Let us check this one whether it is working or not. So, 192. So, suppose I take A as 192 and B as suppose 78, right?
Mm.
So then 192 minus 2 times 78 is how much?
Oh, P P. Okay, we minus. We find 49.
So this is I think actually how much is that? 10.
I multiply with You can, that should be 36.
Yes, 36. Right?
Yeah,
Fine.
yeah.
Okay, so anything, so you cannot, I think, go more, right? So now next is just I'm back calculating the thing. So now 78. So this is, I think, 2 times 36 minus plus 6. So okay, so 6 actually. 78 minus 2 times 36. Yes, I'm just actually creating the example. I'll tell you 1 minute. So okay, so here it is how much? 5 times, right?
Mm.
Yes, so I think this is the example. Let me check. So 5 times 78 minus 2 times 192. Yes, that is 6.
We find the common, greater common is right.
Yes. So this is equals to 6, right? So here this is my A. So this is my B and this is my A.
Mm.
And you can rename it, that is fine. So this is my B, that 5 is my this is my Y, and if I take bracket inside, that is plus of minus 2, so then this is my X. So this is how I can, so 6 you can check that 6 is a
Mm.
common divisor of both A and B, right?
Mm. Mm.
So 6 actually divides A as well as 6 divides B, and 6 divides 192 also.
Mm.
So similarly you can get that this one is, we can express like this form: ax plus by, where
Mm.
x and y are integers.
Mm. Mm.
So this example you are telling about, or anything else you are asking?
Every common divisor of A and B divided.
Yes. So this is an example of the first part. So I will
Yeah,
find a
yeah. The
common
first
divisor.
part is okay. The first part
Yes.
is okay.
So now the thing is every common divisor. So so for example here you can check that 2 is also a common divisor, right? 2 divides A and 2 divides B. So 2 is a common divisor, but I
Mm.
can check that 2 divides 6 also. So every common divisor of A and B divides D also. So that is true also, right?
Mm.
Similarly, here you can check that 3 also divides both of them, and 3 divides 6.
Ah, yeah, it's okay. Mm.
Okay.
Mm-mm. Yeah, yeah. Mm.
Okay. So I think that is fine. Okay. So let us see the how to do the proof. The proof is, so we'll assume that A and B are non-negative. Later we will see how to prove for the negative case. So
Mm.
first we assume that that A is greater than equals to 0 and B is greater than equals to 0, right?
Mm.
Now we use induction to prove. Use induction on n, where n equals to A plus B. So we'll use induction on A plus B. So if n equals to 0, since they are non-negative, A equals to B equals to 0, and then D is 0, right? We take D equals to 0. So there is nothing to do. Now we assume that the theorem is true for 0, 1 up to n minus 1. Up to n minus 1, it is true. By symmetry, you can assume that A is greater than equals to B. So without loss of generality, we can assume that A is greater than equals to B. There is not a problem. Now, if B is 0, now A and B is both not 0, but suppose B is 0, then we take A D to be A and X to be 1 and Y to be 0, right?
Mm.
We're done, right?
Mm.
B is 0, there is not a problem. And if B is greater than equals to 1, then what happens is greater than equals to 1, then we apply the theorem. We apply the theorem for A minus B and B and B, right?
Mm.
So now I know that for both of them it is true, right? So because A minus B plus B is 0, right?
Mm.
So now we can apply them, right?
Yeah.
So then how will it help?
A minus B and B. That's the A minus B is
Yes, I know by induction for the A minus B, the result is true, right?
this C N is right. N
Yes,
equal
yes.
to A
N
minus
is equal
B.
to A plus B. That is fine. That is different.
Oh.
Yes, but the thing is, N, I am induction is on N, but
Mm.
N, I am assuming that is true up to N minus 1,
Oh.
right? So, so now, since A minus B plus B, that is equals to A, that is nothing but N minus B, right? Because A plus B is N, that is less than
Oh.
equals to N minus 1.
Yeah.
So now
Oh.
we can apply induction.
Mm.
So the induction by induction hypothesis,
Mm.
there is a common divisor D of A minus B and B.
Mm. Here, if here the point is this is may not have common divisor, but if have common divisor, this should be the formula is right.
No, the thing is the statement is saying that for any two integers, always there exists a common divisor of this form. That is what the statement says.
Always have common divisor.
Yes, there exists a common divisor that has this
Okay,
form.
okay. It's one. At
Yes,
least
yes.
it's one. Yeah. Mm.
Okay.
Yeah. Mm.
So that's why we can apply induction on the lesser quantity. That is, since this sum is less than equals to n minus 1, I know that there exists a common divisor d of a minus b and b such that I can express like this, right?
Mm. Mm. Yeah.
Okay.
Mm. Mm.
So now, so this d, so the d is a common divisor of a minus b and d divides b also, right? So
Mm.
this implies that d divides the sum also, a minus b plus b also.
Mm.
So this implies d divides a, right?
Mm.
So what happens is that d, now taking consider that d divides a and d divides b. So this implies that d is a common divisor of a and b, right?
Mm. Mm.
Common divisor of a and b. So that is fine. So now we can rearrange our equation. So first we have expressed d equals to a minus b x plus by. So here I can write it ax plus y minus x of b, right? We can rearrange them, right?
A is okay. Why?
Right. So
Mm.
this is my new x and this is my new y, right?
Mm.
So I have expressed that D can be a linear combination of A and B, right?
Mm.
So D is a linear combination of A and B. Okay.
Mm.
So now we have to show the second part, that every common divisor also divides D, right?
Mm.
So suppose E is another common divisor.
Mm.
So suppose E is a common divisor. So E divides A and E divides B, right?
Mm. Mm.
So let us write. So suppose this is some A capital X and capital Y. Let us use, because X and Y will confuse. Plus B.
Mm.
So so this implies E divides their linear combination also. This Ax plus By, right? That is one property we saw, right, in the
Mm.
divisibility conditions. So this is the linearity property. So this implies that E divides D. Right? So any common divisor of A and B, so must also divide D, right? So up to this is fine.
Oh, wait, wait. Let's A device A divide B.
Right.
A
So
is plus by. Hmm? A is plus by. That's okay. But
right.
S and Y here is the same or not the same S and Y
X and
above.
Y we changed it, right? So this is capital X and capital Y. This is X new, and this I am taking as the capital Y.
Hmm? Why we can use the same S, capital S and capital Y here?
No, no. I'm just so I what I want to prove. I want to prove that E divides D, right?
Hmm.
So I can take any combination of A and B, right? So that is the property what I saw in the divisibility, right? So here, right? So if D divides N and D divides N, so this divides for some A and B, right?
Yeah, 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 yeah. But here we use capital S and Y. Is the same or not the above?
Yes, yes. This is same X and Y. This one only. So I'm
It
using such that I can replace D, right? So that is the idea.
the same. Hmm. But in the theorem we just say there exists some S and Y. But
Yes.
how we can map in the S and Y above in below?
No, no. Actually, is yes, yes. That is that I understand what you're saying. So here, actually, what you can do is, so let me write down a few more steps. So E divides A, right? So this implies that A equals to some E times some K1, right?
Mm,
And E divides B. So this implies B equals to some E times K2, right?
mm.
So now if I take this quantity AX plus BY, so I can replace it by E K1X, I can replace A, and it is E K2Y, capital Y, right? So I can take out E common from both of them, K1X plus K2Y. So this implies that E must divide this because it is a factor, right?
So why is E here? This is okay. So
Yes. So this will imply. So this implies that E must divide AX plus B, right? So but that is nothing but D. So D divides D.
why? Mm, A is plus B. Okay. A is plus equal to E multiplied with something.
Yes.
Okay, okay. But it, yeah, yeah, that still makes sense. Yeah.
Yes. So any common divisor,
Mm.
any common divisor of A and B, that must also divide D, because it is a linear
Mm,
combination of A and B. Right?
mm, mm,
Right. Now the condition what you have assumed that A and B are positive. Now what will happen if both are negative? Right?
mm,
So if both A and B are so if A is negative or B is negative, or both can happen.
mm,
So we can apply the result to mod A and mod B, right? Because mod A, that is the absolute value of is positive always, right? So it's because we have proved for positive quantities. So we can apply the theorem to mod A and mod B. So this implies that there exists a common divisor D of mod A and mod B, right?
mm, mm,
Such that B equals to mod AX plus mod BY, right? Now we can adjust our x and y, because we have freedom to choose our x and y, right? So what we can do is, so suppose a is less than 0, right? Then what I can do is I can
mm,
write
mm,
d equals to, this is minus a, right? Then so let me write down. So it is minus modulus of a, and x we can also replace by minus
mm,
x, right?
mm, mm,
Plus b. Let us keep b as it is. So what will happen is, so if a is less than 0, so then we can replace like this, right?
mm.
So
I
now,
get down zero. So minus. We do the negative of s.
yes, so it will be a times of minus x. So you can just replace like this,
Mm,
and mod b of y. But on the other hand, if b is less than
mm,
0, similarly we can do that mod by, that we can replace by b times of minus y,
mm,
and we'll get the condition, because x and y we have flexibility, right, to choose.
mm, mm,
Okay.
mm,
So in all conditions, irrespective of a and b, whether it is positive negative, so we always
mm,
have a common divisor that can be expressed into this linear form,
mm,
linear combination of a and b.
mm.
Okay.
First, I got it. I got it. But I confused about in the proof.
Yes.
We get D is a common divisor, divisor,
Okay.
and other thing also common divisor.
Yes.
First, we can prove other common divisor divided by D is
Okay.
right. That's a strong relation, but what is the difference between D and other divisor in the proof? What the lie? What is the lie?
Yes, yes, that is fine. That I understand what I'm saying. So it is saying that we will find a common divisor that we can express in this linear form, ax plus by. So that is the statement it is saying. So it is not special any condition they are saying. So it is just
Mm,
saying we can find a common divisor such that I can express d like that, ax plus by. And
mm,
once I find this d, any other common divisor will divide d.
mm. But any common divisor can be expressed by the equation
No,
D
that I
equals to
that that we
AX plus
cannot.
Y, BY is
No,
right.
that we don't know. That every common divisor, whether it can be expressed like ax plus by for some x and y. That we don't know.
But about we say in about the previous we we can see that if you scroll up, scroll
Yes,
down,
yes.
we have a linear relation. If D is any divisor of A and B, we can express like D equal to AS plus BY, right?
How?
Mm, you can scroll in the property of divisor.
Yes.
Here, linearity.
Hmm.
No, no. This is not equal.
Yes, yes. It is.
The difference is equal. Yeah.
Yes, yes. That is the difference.
Okay, okay. I I thought this is equal.
Yeah.
Okay.
So you know that d divides that combination, but
Ah,
it is not equal always.
the different. This the command D is that's equal.
Right.
Yeah, yeah. Okay. Other we should be take the divisor. Yeah. Okay.
Okay.
Okay, got it. Yeah, yeah, yeah. You see the different.
Okay. So the next theorem that it says is, so given integers a and b, so there is one and, okay, let me write down. So there is one and only one, a number d with the following properties. So there is a unique d with the following properties. So the first property is that d is non-negative, greater than equals to 0. The second property is that d is a common divisor. D divides a and d divides b. And the third property is e divides a. Suppose e is another common divisor. So this implies that e must also divide d. So there is only one unique such divisor that is there, which satisfies all the three conditions. So the third condition says that every common divisor divides d. Okay.
Hmm. D D E E given integer one and only one number D.
Right.
Different. This took the same of pivot theory.
Yes, the previous is yes. So here it actually extra condition that we are saying is it is uniqueness, but uniqueness only comes from the condition is that we are taking is the d is non-negative, because for the example what you saw here is right. So here 6 is divide both of them, but minus 6 also divides both of them, right?
Mm.
Minus 6 also satisfy both conditions. That minus 6 I can express like this because I will just enter minus
Mm.
here and minus here.
Mm. Mm.
And every common divisor will also divide minus 6. But the uniqueness comes when I add this extra condition that d has to be
Mm. 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 Yeah, yeah, yeah. Mm.
right.
Mm.
So the by previous theorem, we can say that at least one d exists that satisfy this b and c condition. That is what the previous theorem says, right? But
Mm.
minus d also satisfies the condition. So when we restrict this condition, we will have uniqueness.
Mm.
It is yes. So that is the theorem. Just statement. So this gives you actually the thing, the greatest common divisor. So if you take the positive d
Mm.
such that b and c property hold, then that is called the greatest common divisor. So that is the definition. So the number D in the previous theorem, that is, it should satisfy all the three conditions, is called the greatest common divisor. Right.
Mm.
So here we can of A and B. So it is denoted by A comma B. Right. It's denoted by this thing. So one more definition is that if the GCD is one, the greatest common divisor short form is GCD, then A and B are said to be relatively prime.
Mm.
Fine.
Mm. Yeah.
Right.
Mm.
So now, right. So now there is some properties of this GCD. So let us see the properties. The first one is the GCD of AB. That is same of GCD of B comma A, right? That is obvious.
Mm.
Okay.
Mm.
GCD of AB and GCD of B are same. The second property is if we take find the GCD of B and C and
Mm.
then find GCD of those A along with that new number, that is same as first finding the GCD of AB and then finding GCD with that and C. Okay.
Mm. Mm. Let's see the great common divisor of three.
Yes. No. No. That is different. That will be different.
Okay. PC great GCD of PC, and after that we check. For example, the previous example, we check that we have a six and
Correct.
six with A is right.
Yes. Yes. GCD is six. So A is 192 and 78. So
Mm.
that example. Uh, right. So their GCD is six.
Six,
Right.
and A, for example, A equal to tail. So
Okay.
the result is 3.
Oh no, no, I didn't understand. What are you taking A as?
For example, A equal to tail, B equal to 192, and C equal to 78.
Okay. So
So
this
the
is your
B, the C, and A equal to tail. In the
okay.
number 2 property, we
Yes, yes. So
the
then
result
the
is
right hand side,
3.
what I have is
A equal to tail, not 10.
how much I don't understand.
Tail, 1, 2.
Oh, 12. Okay.
Tail, yeah.
This and then BC is 6, right? So the right hand side
Mm,
this will give us 6, right?
3.
6. GCD is 6 actually.
Sit.
Same will get here. So A is 12 means so 12 and 192. So that you have to
Mm,
calculate how much is the GCD.
that maybe 6. I'm not sure what.
Yes, let me just check.
The algorithm would be we track the grid minus to lesser
Yes,
is
this is
right.
actually 12. The GCD is 12. So
Mm,
12 and this is 78. So that is also 6.
yeah, okay. mm,
Fine.
mm, mm, mm.
Right. So next property what you have is, so this property is clear, right?
Yeah, yeah, yeah. Mm,
So the third property is, suppose GCD of AC and BC, that is they have already something in common. That is nothing but modulus of C times GCD of AB. Right. So we'll
mm,
take the absolute value of C outside, because the GCD we are always taking the positive thing, right? Non-negative thing.
mm,
Okay.
mm, mm.
Yes.
Yeah, yeah. Mm,
The fourth property is simple. That is the GCD between 1 and A. That is always 1. That's
mm,
same between A and 1. That is 1.
mm.
Fine.
Yeah, yeah.
Right. So these are the properties. So the next theorem. So it is called the Euclid's lemma.
Ah, Euclid. Mm.
Okay. So it says that if A divides BC and GCD of A and B is 1, then A must divide C.
Mm,
So is the statement clear?
yeah, yeah.
So proof is not very difficult.
Mm,
So it is saying that since GCD is 1 between A and B, right? So we can express, so we can write 1 as AX plus BY. That is the theorem gives us, right? For
mm,
some integer x and y, right?
mm,
So that is by the theorem. So now we can just multiply with C on both sides.
mm,
So I get C equals to ACX plus BCY, right?
mm,
So right. So I know. Okay. Now we'll use this condition. So
mm,
A divides BC, right?
mm,
So BC equals to some A times K, right?
mm,
For some K in integers. So this I can replace. So ACX BCY I can replace is at some AKY, right?
mm,
So if I take A common, then it's CX plus KY.
mm, mm,
So this will imply that A divides BC.
mm. Yeah, yeah, yeah.
So this is fine, right?
Yeah, yeah. It's okay. Mm,
Okay. So okay. So then this ends this get us this section. Next one is prime numbers. So maybe we can start.
mm, mm.